Article 310.15 B4 of the National Electrical Code addresses situations where the neutral conductor is not required to be considered a current carrying conductor for ampacity adjustment purposes. This provision is particularly relevant in systems such as the 120/240-volt three-phase open delta configuration, where the neutral conductor's role differs significantly from that in a standard Y-connected system. To fully understand the application of this article, one must first grasp the fundamental characteristics of an open delta system and the specific function of its neutral conductor. In a three-phase system, the standard configuration is typically a Y or delta connection. However, an open delta, also known as a V connection, represents a unique arrangement where one of the transformer windings is omitted from the delta configuration. This results in a system that can still provide three-phase power, albeit with a reduced capacity compared to a full delta system. The open delta configuration is often used in situations where the full capacity of a closed delta is not initially required, but there is an anticipation of future load growth. It allows for a more economical initial installation, with the option to later add the third transformer to complete the delta and increase the system's capacity. The neutral conductor in a 120/240-volt open delta system plays a crucial role in providing a stable reference point for single-phase loads, such as lighting and receptacles, which are connected between the phase conductors and the neutral. However, unlike in a balanced three-phase Y system where the neutral conductor carries the imbalance of the three phases, in an open delta system, the neutral typically does not carry significant current under normal, balanced operating conditions. This is because the single-phase loads are usually distributed in a way that minimizes current flow in the neutral. Therefore, Article 310.15 B4 recognizes this characteristic and allows for the neutral conductor not to be counted as a current carrying conductor when determining the ampacity directing factors for conductors in a raceway or cable. This is a significant advantage as it can potentially reduce the required size of the conductors and the conduit, leading to cost savings and easier installation. However, it is imperative to ensure that the system is properly designed and balanced to minimize any potential current flow in the neutral conductor. If the single-phase loads are not evenly distributed, or if there are significant harmonic currents present, the neutral conductor may indeed carry a substantial amount of current, in which case it would need to be counted as a current-carrying conductor. Furthermore, it is crucial to consider the potential for future load growth and to design this system with sufficient capacity to accommodate any anticipated increase in single-phase loads. If there is a possibility that the neutral conductor will carry a significant amount of current in the future, it is prudent to count it as a current-carrying conductor from the outset. Table 310.15 B2 of the National Electrical Code, on the other hand, provides adjustment factors for the ampacity of conductors in a raceway or cable based on the number of current-carrying conductors. This table is generally applicable to systems where the neutral conductor is expected to carry a significant amount of current, such as in a three-phase 4YY system with nonlinear loads. In such systems, the harmonic currents generated by the nonlinear loads can cause the neutral conductor to carry a substantial amount of current, potentially exceeding the current in the phase conductors. Therefore, Table 310.15 B2 requires that the ampacity of the conductors be adjusted to account for the increased heating effect caused by the multiple current-carrying conductors. However, in the case of a 120/240-volt three-phase open delta system where the neutral conductor is not expected to carry a significant amount of current, Table 310.15 B2 is not applicable. This is because the neutral conductor is not contributing to the overall heating of the conductors in the raceway or cable. Therefore, it is not necessary to derive the ampacity of the conductors based on the number of current-carrying conductors. It is important to note that the application of Article 310.15 B4 and Table 310.15 B2 depends on the specific characteristics of the system and the expected current flow in the neutral conductor. A thorough understanding of the principles of three-phase power, the characteristics of open delta systems, and the potential for harmonic currents is essential for making an informed decision. In addition to the NEC requirements, it is also important to consider any local codes or regulations that may be in effect. Some jurisdictions may have specific requirements for the sizing of neutral conductors in open delta systems, or they may require that the neutral conductor be counted as a current carrying conductor regardless of the expected current flow. It is always advisable to consult with a qualified electrical engineer or inspector to ensure that the installation is in compliance with all applicable codes and regulations. Furthermore, it is crucial to properly document the design and installation of the system, including the calculations used to determine the ampacity of the conductors and the rationale for not counting the neutral conductor as a current carrying conductor. This documentation can be invaluable in the event of future inspections or modifications to the system. In summary, Article 310.15 B4 of the National Electrical Code applies to 120/240 volt three-phase open delta systems where the neutral conductor is not required to be counted as a current carrying conductor. This allows for a more economical installation, as it can potentially reduce the required size of the conductors and the conduit. However, it is imperative to ensure that the system is properly designed and balanced to minimize any potential current flow in the neutral conductor. Table 310.15 B2 is not applicable in the scenario, as it applies to systems where the neutral conductor is expected to carry a significant amount of current. A thorough understanding of the principles of three-phase power, the characteristics of open delta systems, and the potential for harmonic currents is essential for making an informed decision. Always consult with a qualified electrical engineer or inspector to ensure compliance with all applicable codes and regulations. The proper application of these NEC articles hinges on a clear understanding of the system's load characteristics and the expected behavior of the neutral conductor. To elaborate further, let's delve into the specific factors that influence the neutral current in an open delta system. One significant aspect is the balance of single-phase loads connected to the system. Ideally, these loads should be distributed as evenly as possible across the two energized phases of the open delta. A significant imbalance in these loads will inevitably lead to current flow in the neutral conductor, as it becomes the return path for the unequal currents. This imbalance can arise from various sources, such as unevenly distributed lighting circuits, unequal appliance usage in different parts of a building, or variations in the power demands of different pieces of equipment. To mitigate this issue, careful planning and load management are essential during the design and installation phases. This may involve strategically distributing circuits to ensure a more balanced load profile or implementing load shedding strategies to reduce peak imbalances. Another factor that can contribute to neutral current is the presence of nonlinear loads. These loads, which include devices like electronic ballasts, computers, and variable frequency drives, draw current in a non-sinusoidal manner, generating harmonic currents that can flow back to the source through the neutral conductor. Unlike fundamental frequency currents, triplet harmonics, such as the third, ninth, and 50th harmonics, are additive in the neutral of a three-phase system. This means that even a small percentage of triplet harmonics in each phase can result in a significant harmonic current in the neutral conductor. In an open delta system, the impact of harmonic currents on the neutral can be particularly pronounced due to the absence of the third transformer winding that would typically help to mitigate these currents in a closed delta configuration. To address the issue of harmonic currents, several mitigation techniques can be employed. These include the use of harmonic filters, which are designed to block or divert harmonic currents, and the specification of harmonic rated equipment, which is designed to minimize the generation of harmonic currents. Additionally, the use of separate neutral conductors for nonlinear loads can help to isolate harmonic currents from other parts of the system. Furthermore, it is important to consider the grounding of the open delta system. A properly grounded system is essential for safety and for ensuring the proper operation of protective devices. The grounding electrode conductor should be sized in accordance with the NEC and should be connected to a suitable grounding electrode, such as a ground rod or a metal water pipe. The neutral conductor should also be bonded to the grounding electrode at the service entrance to provide a low impedance path for fault currents. In addition to the factors mentioned above, It is also important to consider the voltage drop in the neutral conductor. Excessive voltage drop can lead to poor voltage regulation at the load end, which can affect the performance of sensitive electronic equipment. To minimize voltage drop, the neutral conductor should be sized appropriately and should be installed with short, direct runs. Regular monitoring of the neutral current is also recommended to ensure that it remains within acceptable limits. This can be accomplished using ammeters or clamp-on meters. If the neutral current is found to be excessive, steps should be taken to identify and correct the underlying cause, such as load imbalances or harmonic currents. The NEC provides guidance on the sizing of conductors and the installation of electrical equipment. However, it is important to remember that the NEC is not a design manual. It is a set of minimum safety standards that are intended to protect people and property from electrical hazards. The design of an electrical system should be performed by a qualified electrical engineer who has the knowledge and experience to ensure that the system is safe, reliable, and efficient. In the case of a 120/240 volt three-phase open delta system, the engineer should carefully consider the load characteristics, the potential for harmonic currents, and the grounding requirements to ensure that the system meets all applicable codes and regulations. In conclusion, the application of Article 310.15 B4 and Table 310.15 B2 to a 120/240 volt three-phase open delta system requires a thorough understanding of the system's characteristics and the expected behavior of the neutral conductor. By carefully considering the factors discussed above, it is possible to design and install a safe and reliable electrical system that meets all applicable codes and regulations. Let's further investigate the nuances of applying the National Electrical Code in this context. Firstly, it's paramount to understand that electrical codes are not static. They are periodically updated to reflect advancements in technology, improved safety practices, and lessons learned from past incidents. Therefore, always refer to the latest edition of the NEC adopted by your jurisdiction. Secondly, remember that the NEC provides minimum requirements. In many situations, exceeding these minimums is prudent to enhance safety, reliability, or future capacity. The decision to treat the neutral as a current carrying conductor, even when not strictly required, could be a worthwhile investment, particularly if future load changes are anticipated. Thirdly, consider the role of the authority having jurisdiction, or OJ. This entity, typically a local building inspector or electrical inspector, has the final say on code interpretation and enforcement. Consulting with the ASJ early in the design process can prevent costly rework later on. Fourthly, documentation is critical. Maintain detailed records of all calculations, design decisions, and code interpretations. This documentation is invaluable for inspections, future modifications, and troubleshooting. Fifthly, remember that the NEC is not a substitute for sound engineering judgment. Code compliance is necessary but not sufficient for a safe and reliable electrical system. Consider factors such as voltage drop, conductor heating, and fault current protection, which may not be explicitly addressed by the code. The sixth point to consider is the impact of energy efficiency standards. Many jurisdictions have adopted energy codes that require the use of energy-efficient lighting, motors, and other equipment. These standards can impact the design of the electrical system and may require the use of different wiring methods or equipment. Seventh, explore the use of modeling software. Several software packages are available that can simulate the performance of electrical systems, allowing engineers to identify potential problems before they occur. These tools can be particularly helpful in complex systems with nonlinear loads or unbalanced conditions. Eighth, remember the importance of proper installation. Even the best design can be compromised by poor workmanship. Ensure that all electrical work is performed by qualified electricians who are familiar with the NEC and best practices. Ninth, consider the impact of power quality. Power quality problems, such as voltage sags, swells, and harmonics, can damage sensitive electronic equipment and disrupt operations. Implement power quality monitoring and mitigation techniques as needed. 10th, always prioritize safety. The electrical work is inherently dangerous, and it is essential to follow all safety precautions. Where appropriate, personal protective equipment, de-energize circuits before working on them, and verify that circuits are de-energized before touching them. The open delta configuration, while offering cost savings in initial installation, demands careful consideration of several factors. Firstly, the voltage regulation in an open delta system tends to be poorer compared to a closed delta or Y-connected system. This means that the voltage at the load terminals can fluctuate more significantly with changes in load. This is due to the higher impedance of the open delta transformer configuration. To mitigate this, consider using larger conductors to reduce voltage drop and ensure that the transformer is sized appropriately for the expected load. Secondly, the available volt current in an open delta system is typically lower than in a closed delta system. This can affect the selection of overcurrent protective devices, such as circuit breakers and fuses. Ensure that the selected devices have adequate interrupting ratings and that the coordination between devices is properly designed to prevent nuisance tripping. Thirdly, the open delta configuration is more susceptible to voltage imbalances than a closed delta or Y-connected system. Voltage imbalances can cause overheating in motors and other equipment. To minimize voltage imbalances, ensure that the single-phase loads are evenly distributed across the two energized phases and consider using voltage monitoring equipment to detect and correct any imbalances. Fourthly, the open delta system is more sensitive to transformer failures. If one of the two transformers in the open delta configuration fails, the system will be unable to provide three-phase power. Consider using redundant transformers or implementing a backup power system to ensure continuity of service. Fifthly, the open delta system may not be suitable for all types of loads. Some loads, such as large motors or welding equipment, may require a more robust power source than an open delta system can provide. Consider the specific requirements of the loads being served when selecting the transformer configuration. In addition to these considerations, it is also important to be aware of the potential for ferroresonance in open delta systems. Ferroresonance is a phenomenon that can occur when a transformer is energized with a high impedance source and a nonlinear load. This can lead to overvoltages and overheating in the transformer. To prevent ferroresonance, ensure that the transformer is properly sized and that the source impedance is not too high. Furthermore, the NEC requires that all electrical equipment be listed and labeled by a recognized testing laboratory. This ensures that the equipment has been tested and meets applicable safety standards. When selecting electrical equipment for an open delta system, ensure that it is listed and labeled for the intended application. Moreover, remember that the design and installation of an electrical system is a complex process that requires the expertise of qualified professionals. Always consult with a licensed electrical engineer and a qualified electrician to ensure that the system is safe, reliable, and compliant with all applicable codes and regulations. Electrical safety is of paramount importance. Always follow safe work practices and use appropriate personal protective equipment when working on or near electrical equipment. Never work on energized circuits unless absolutely necessary, and always de-energize circuits before working on them whenever possible. The complexities associated with the neutral conductor in open delta systems necessitate a deep dive into practical considerations. Let's explore several real-world scenarios that highlight the importance of proper understanding and application of the NEC guidelines. Firstly, consider a small commercial building supplied by a 120/240 volt open delta system. The building houses a mix of lighting, receptacles, and small HVAC equipment. During the initial design phase, the electrical engineer carefully calculates the expected load and determines that the neutral conductor will not carry a significant amount of current under normal operating conditions. Based on this assessment, the engineer applies Article 310.15 (V4) and does not count the neutral as a current carrying conductor. However, several years later, the building undergoes a renovation. New tenants move in, and the load profile changes significantly. The building now houses a computer lab with a large number of nonlinear loads. As a result, the neutral conductor begins to carry a substantial amount of harmonic current. The increased current causes the neutral conductor to overheat, leading to a potential fire hazard. In this scenario, the initial assessment was no longer valid due to the change in load profile. The engineer should have reassessed the situation and considered counting the neutral as a current carrying conductor. Secondly, consider a rural residence supplied by a 120/240 volt open delta system. The residence is located at the end of a long distribution line. The voltage regulation is poor, and the voltage fluctuates significantly with changes in load. The homeowner installs a solar photovoltaic system to reduce their electricity bill. However, the solar inverter introduces harmonic currents into the system. The harmonic currents cause the neutral conductor to overheat, leading to a potential fire hazard. In this scenario, the poor voltage regulation and the introduction of harmonic currents from the solar inverter combined to create a hazardous situation. The homeowner should have consulted with a qualified electrician to ensure that the solar system was properly installed and that the neutral conductor was adequately sized. Thirdly, consider a manufacturing facility supplied by a 120/240 volt open delta system. The facility uses a large number of single-phase motors. The motors are not evenly distributed across the two energized phases. As a result, the neutral conductor carries a substantial amount of imbalanced current. The imbalanced current causes the neutral conductor to overheat, leading to a potential fire hazard. In this scenario, the unbalanced load caused the neutral conductor to overheat. The facility should have redistributed the motors across the two energized phases to balance the load. In each of these scenarios, a failure to properly consider the characteristics of the open delta system and the potential for neutral current led to a hazardous situation. These scenarios highlight the importance of a thorough understanding of the NEC guidelines and the need for ongoing monitoring and assessment of the electrical system. To further enhance safety and reliability, consider implementing the following best practices. Firstly, perform a load study to determine the expected load profile and the potential for neutral current. Secondly, use a harmonic analyzer to measure the harmonic content of the current in the neutral conductor. Thirdly, install a ground fault monitoring system to detect and prevent ground faults. Fourthly, perform regular inspections of the electrical system to identify potential problems. Fifthly, train employees on electrical safety and the proper use of electrical equipment. By implementing these best practices, you can significantly reduce the risk of electrical hazards and ensure the safe and reliable operation of your electrical system. Remember, electrical safety is everyone's responsibility. Be aware of the potential hazards and take steps to protect yourself and others. The nuances of open delta systems extend beyond the neutral conductor and impact various aspects of electrical system design. Let's delve into some additional considerations that are crucial for ensuring safe and efficient operation. Firstly, the transformer selection is paramount. When choosing transformers for an open delta system, it's essential to select units that are specifically designed for this configuration. Standard transformers intended for closed delta or Y connections may not be suitable and could lead to performance issues or even failure. Open delta transformers typically have special winding configurations and impedance characteristics to optimize their performance in this unique arrangement. Secondly, the overcurrent protection scheme needs careful attention. The available fault current in an open delta system is generally lower than in a comparable closed delta system. This means that standard overcurrent protection devices such as circuit breakers and fuses may not operate as effectively in clearing faults. It's crucial to perform a thorough fault current study to determine the available fault current at various points in the system and select overcurrent devices with appropriate interrupting ratings. Additionally, coordination studies are essential to ensure that the overcurrent devices are properly coordinated to prevent nuisance tripping and selectively isolate faults. Thirdly, grounding is a critical safety aspect. Proper grounding is essential for providing a low impedance path for fault currents and minimizing the risk of electric shock. The grounding system for an open delta system should be designed in accordance with the NEC and should include a grounding electrode system, a grounding electrode conductor, and equipment grounding conductors. The neutral point of the open delta system should be bonded to the grounding electrode system at the service entrance. Fourthly, voltage regulation needs careful consideration. Open delta systems tend to have poor voltage regulation compared to closed delta or Y systems. This means that the voltage at the load terminals can fluctuate more significantly with changes in load. To mitigate this, consider using larger conductors to reduce voltage drop and ensure that the transformer is sized appropriately for the expected load. Voltage regulators can also be used to maintain a stable voltage at the load terminals. Fifthly, harmonic mitigation strategies may be necessary. Non-linear loads, such as electronic ballasts, computers, and variable frequency drives, can generate harmonic currents that can flow back into the electrical system. These harmonic currents can cause a variety of problems, including overheating of conductors and transformers, voltage distortion, and equipment malfunction. Harmonic filters can be used to mitigate harmonic currents and improve power quality. In addition to these considerations, it's also important to be aware of the potential for single phasing in open delta systems. Single phasing occurs when one of the phases is lost, leaving the system operating on only two phases. This can cause motors to overheat and potentially fail. To prevent single phasing, consider using phase loss relays that will trip the circuit breaker if a phase is lost. Electrical systems demand a multifaceted understanding encompassing design principles, safety protocols, and adherence to regulatory standards. The information is intended for educational purposes and should not be considered a substitute for professional engineering advice. Always consult with qualified professionals for specific applications.